Okay, so you have, let's say question one. So question one is basically on your chi-square test. Okay. So chi-square distribution, right? So you're asked to find the critical values. It's strange scribblings. Strange. Why are these things appearing on my screen? I'm not doing that. Or is somebody able to do simultaneous screen presentation? Anyone doing that?
No, doctor.
Oh, not sure. I didn't draw all those things just now. It just appeared on my screen. Okay. So finding critical values for different degrees of freedom, right? So your chi-square distribution, the shape of your chi-square distribution is controlled by different a parameter called degree of freedom, df, right? So for different degrees of freedom, it has a different shape. Okay. So finding the critical value will be, so you have to check the statistical tables, right? So I think this one should be no problem for everyone.
Yes, doctor.
Okay, it's basically just this 1 and 2 you can actually find from the test table. You can check it with the solution later. Comment on changes in the critical value for fixed alpha, but with with increased df, right? So basically, when you increase the df, let me see if I can draw something here. Okay, so let me see. Okay, so basically, you have your oops. Let's see this. It's not so easy to use writing on the board here. So basically, your degree of freedom, right? It will, for 1 degree of freedom, it will look something like this. Okay. So as you have more degrees of freedom, your chi-square distribution will start to have look something like this. Okay, like a hump and then with a tail, right? So this one maybe df equals to 1. So this degree of freedom is maybe something like 9. Okay. So to get the 5%, right? So you have a cutoff here. Okay. So this one you also have a sort of like I have to move this around. So you also have a sort of like a cutoff here, right? To get 5%, right? So of course you see that okay, so here's a 5%, right? So of course you see that for this case, when the degree of freedom is large, your your critical value will go to the right-hand side, right? Okay, so even if you you can check the tables and you can actually see that, all right? Okay. Then part B, a chi-square goodness of fit test has an observed statistic of 3.72. 5 categories and 2 parameter models are estimated, right? So then given this information is the statement the p-value is larger than 5%, true or false? So first thing we need to decide about the chi-square test is the degree of freedom, right? So for this case, what is the degree of freedom?
4.
4.
4. Why do you say it's 4?
Because we're comparing with 5 categories.
No, it's not 4. The degree of freedom of the chi-square test is equal to, I think I should switch to the drawing board. Okay, let me just move. So the degree of freedom of the chi-square test, right, is equal to the number of categories subtract the number of estimated parameters then subtract 1. Okay. So here in this case, you have 5 categories. You have 2 estimated parameters and then subtract 1. So you should have 2 degrees of freedom only. Okay. You missed out this part. I'm not sure if, how are you taught? About this part. This is the general result for calculating the degree of freedom of your chi-square test. I know that a lot of textbooks, they just simply write this. Right? Just count the number of categories, subtract 1, right?
Yes.
But
Yes.
this is assuming that you don't have any estimated parameters. So in this case, basically it is like number of categories, subtract 0, subtract 1. There's an assumption. When you use this result, it is assuming that there are no estimated parameters. Okay, so the exact one is this one, right? I'm saying this because in different situations, the degree of freedom, the way you calculate it is slightly different, right? For example, if you do the goodness of fit, for example, you have some distribution, right? For example, if you want to fit Poisson data, a Poisson model, right? So these are your observations, 0, 1, 2, 3, maybe 4 or more. And let's say this is your frequency, okay? You observe 25, 12, 9, 6, 3, okay? For example. Then you want to find the, so this is your observe, right? Sorry, this is your count. So your frequency is the observed count, right? This is your O. And then you have the expected count, right? In the expected count, you have to find the probability of the Poisson, right? Multiply by the sample size here, n. Okay, that's your expectation. Then you can do observed minus expectation squared and so on, right? To calculate your chi-square statistic. So this probability is right. Like for example, px of 0 here, you have to calculate it using this, right? For the Poisson model, okay? Now, where do you get this parameter? This is the mean parameter in the Poisson model, right? So you estimate this using the sample mean here, right? So for example, 0 times 25 plus 1 times 12 and so on, right? So that's the sum. And then you divide by the sample size, right? So this will estimate. So basically, you're estimating one parameter. So in this case, if you do the Poisson, so if you use the goodness of fit, right? Your degree of freedom will be equal to, you have got how many categories have you got? 1, 2, 3, 4, 5. Okay? And then you will lose 1 degree of freedom. In this case, because you're estimating one parameter, all right? And then subtract 1 again. So here, your degree of freedom is actually 3, okay? The common mistake is students forget to subtract the degree of freedom due to estimation of parameters, all right? The simpler type of chi-square test where you basically just have categories, subtract 1 is in a situation where that you don't have to estimate any parameters because all the values are given already. For example, in some situations, like for example, when you want to test for proportion, right? Say you have 3 types of things, A, B, and C, okay? They occur with probably with this following proportions, 0.3, 0.2, and just 0.5, right? So then you have your observed count. Maybe this is 35, this is 25, and therefore this one is 40, okay? Then your expectation will be, so the total is 100 here, 100 here, right? So the expectation will be this probability multiplied by n, okay? So you will get 30, 20, and 50, okay? Right, and then you can calculate your observed minus expected squared and so on, okay? In this case, the number of categories that you have got is 1, 2, 3, right? So the degree of freedom is 3. Subtract, okay, how many parameters have you estimated here? None, right? There's no estimation involved, isn't it? You don't use the data to actually estimate any parameter because these numbers have already been given. No need to estimate, right? So there's actually no loss here. And then you subtract 1 degree of, subtract 1 at the end, right? That's why in the usual case, you always kind of like, you kind of like feel like it's always number of categories, subtract 1, with forgetting about this part, right? So, but then I'm telling you the general form has, you have to subtract estimated parameters. It's just that in a lot of situations, you don't actually have the estimated parameters component, okay? That's why you only see that it's number of categories subtract 1. Okay? So, right, so going back to this part here, therefore over here, your degree of freedom is 3, right? So then you have to check the table, yeah? So what does the table say? So your degree of freedom in that case was 5 subtract 3, sorry, subtract 2, subtract 1, right? Actually 2. So your chi-square distributed density might look something like this, okay? So
7.815.
So here it says you observe 3.72, right? Okay, the p-value is this part, right? Okay, your chi-square is 2 degrees of freedom. So what is this probability, right? Now, in the table, you will not be able to find this, okay? Because the table will only give you like 5%, what's the cutoff and all that, right? So you check the table and can you find the cutoff for 0.05 for 2 degrees of freedom. Somebody check this.
5.991.
Sorry?
5.991.
5.991, right? So it's here, right? 5.991 will give you 0.05, okay? Therefore, can you tell me what is the p-value of the test when you observe 3.72? Is it more than 5% or less than 5%?
More.
More, right? Because your piece is this large piece here, okay? You know that 5.991 onwards, this piece is 5%. Now you are starting at 3.72. So your piece is actually larger than 5%, all right? So therefore, the statement that's given, right? So the statement is given here is true, yeah? Okay, this is how you decide. Okay. Right, any more queries about this?
No.
No.
Okay, I think 2 we can actually skip this. Okay, this is actually quite easy to do. These are your observed frequencies, right? And your under the null hypothesis, all the colors have equal preference, right? So you got 5 types of colors. So it's the probability for each type will be 1 out of 5. So then you multiply by the total sample size, right? You have to calculate that. Okay, then you can get your expected frequencies, and then you can find your chi-square statistic. Okay, this should be quite simple. For example, so you have observed and expected, right? So 310, 292. So what's the total here? Can somebody calculate this?
One 1394.
Sorry,
394.
1394. Okay. So here, if you assume that the null hypothesis is that the colors are equally likely to be preferred by customers. Okay. So you want to see whether the data actually agrees with this hypothesis. So if this hypothesis is true, then you expect that it will be equally divided, right? So 1394 over 5, right? Okay. So all of them are the same. That's expected. So then you have observed minus expected square, right? So then you take the difference and then you square, okay? All right. So then your chi-square statistic will be you add up everything, okay? Sorry, not yet. So then you have to, let me see. Not yet. So you have to divide by E, the expected. So after you calculated this, you divide by E, okay? Divide by the expectation. So you get a bunch of numbers here. And then after that, you add up all of them. And this will be your chi-square test statistic, all right? And then you can go and check the the chi-square table with the appropriate degree of freedom. What's the degree of freedom here?
4.
Yeah, 1, 2, 3, 4, 5. There are 5 categories. There are no estimated parameters. That no need to estimate any parameters. So subtract 0, subtract 1, so 4. Okay. Okay, test the null hypothesis at 1% level of significance. So basically, you have to find chi-square 0.01 at 4 degrees of freedom, right? So find this critical value, okay, and then compare, right? See whether your observed test statistic falls in the is larger than the critical value or not. Okay. The chi-square test, there's only it's only one-sided on the right-hand side. There's no two-sided chi-square test. Okay. Because we want to basically see the fit, right? If your data is fitting your expectation very well, then basically these values will be all close to 0. Okay. And your chi-square value will be very small, right? So you won't reject the null hypothesis. On the other hand, if what you see is very different from what you expect, then the difference after your square will be large, right? And when it is large, your chi-square statistic will become large, right? So when it is sufficiently large, so how do you determine whether it's sufficiently large or not? Therefore, you need a cutoff, okay? And that cutoff is obtained from the critical value, right? So once your test statistic exceeds the cutoff, the critical value, then you consider it to be large enough that what you actually observe, right, does not match what you expect. So therefore, your null hypothesis is probably wrong. Okay. Right. So you can actually do this test. Now, when you do the conclusion, right, generally, I know that students will generally just say reject, don't reject, okay? But it is better that you, after you say so, if you reject the null hypothesis, then you have to, it is better that you show what are the estimated proportions, okay? So in this case, you just show the estimated proportions. Which one is actually more than what you expect, right? You, under the null hypothesis, you expect equal, so there will be 0.2, right? But you could actually estimate, the things, okay? For example, you could find 310 divide by the total, right? What was the total? 1394, is it? Okay, so and so on, right? So for example, you could find its estimate, and then you can actually comment that which one is actually higher, all right, than expected, and which one is lower than expected. Okay, that will give the conclusion a richer richer interpretation, rather than you say reject, don't reject. Okay, that's very simplistic. Yeah. In fact, we know that color of packaging is actually a factor for sales volume, right? So it's not surprising that we reject this null hypothesis. Different products, generally customers prefer different kinds of packaging color, okay? For example, you want to sell things that are more for the men, then usually the packaging will be going more towards the blue that kind of color, right? Blue, white. Okay. For women, maybe more on pink, red. Okay. It also depends on what sort of things you're selling, right? You're selling like formal things, then usually is a black color, right? You're selling like funny things, and then usually use some kind of pastel color will be more popular, right? Okay. And then how about question 3? Is it okay? Question 3. Okay, so let's look at question 3. So this is trying to see whether what sort of whether there's an association between developing breast cancer and the age at which a woman has the first child, right? So you have this is actually a real data, yeah. Okay, more than equals to 25, because breast cancer is primarily a cancer that's related to hormones. Okay, so so it is thought that when a woman has a child, might actually affect subsequent development, right? When a woman bears a child, her body undergoes a very big hormonal change, and these hormonal changes sometimes can. It is suspected that these hormonal changes, if it occurs at different times of a woman's life, it can actually increase later development of breast cancer, right? So then they collected this data. Okay. Right, very simple data, right? So then you can count the column marginals, right? So these are your marginals. So this one is your column marginal, right? So column marginal. Marginal means the you just collapse the table into one dimension, right? So this will be 6, 9. This one is 2, 7. Okay. All right. So here, this one is 8, 2, 1, 6. Right. And this one is 0, 3, right, 8. Okay. Actually, so there's actually a typo in the question paper. The question paper says 6188, right? It should be 6168, yeah? So please correct that. Okay? Right, that's your column marginal. So then you are asked to find, sorry, first part is you're asked to find the, so write down the null and alternative hypothesis, okay? So your null will be the two variables are not associated, right? H as first child is independent, okay, of subsequent breast cancer, right? Your alternative will be is not independent, okay? It's very simple. The now is always independent, right? The alternative is the opposite, okay? And compute the expected values for each cell, so you know how to compute that, right?
Yes.
So take the row. So this one is the row marginal. So here 1268, right? Then multiply by 96, then divide by 6158. Okay. So you basically like for this cell, you take this row, the row marginal, multiply by the column marginal, right? And then you divide by the sample size. Okay. That will give you an expected value. And then you do for all of them, right? And then part C, you can calculate the chi-square test statistic, which is basically you take the observed value here and you subtract this part, right? Then you square it and then you divide by the expectation again, okay? So you will get your chi-square value. If you do that carefully, you should find that your chi-square test statistic is, let me check, what is it? So about 19.325, okay? So you get about 19.325. And how many degrees of freedom are there?
1.
Sorry, I think this is not correct. This should be 1.77, sorry. That was for the previous one. Okay, you'll get something close to 1.77, okay? So the degree of freedom for this chi-square test is 1 because it's the number of rows subtract 1 times the number of columns subtract 1, okay? Actually, this degree of freedom comes from the generic form, which is number of categories subtract number of estimated parameters subtract 1. So it's actually obtained from that. But so if you're taking a more advanced statistical course, then they will. It's basically just some kind of algebra. So, but then I will not go through the algebra with you, right? Not necessary, okay? But just to let you know that in case you are curious, why is there such a nice formula? Like it's actually coming from this general result, right? And after some rearrangement, it has that nice form, okay? At this level, you can just use it as it is, okay? Right, then after that, you are asked to, so you do the statistical test. So the chi-square value at 1 degree of freedom, 0.05, alpha 0.05 is 3.841, right? So 1.77 is below 3.841, right? So there's not enough evidence, right, to reject the null hypothesis, okay? right? So not enough. But however, it will be interesting to follow up the analysis a little bit more. Now we can actually calculate the probability, right, of the probability of developing breast cancer for the age group of more than 25, right? So this will be 31, okay, 31 of them out of 1628, right? And for the other group, right, is 65 out of 4530, okay? We focus on the group, yeah? And then your relative risk is basically just the ratio of these two values, right? Take, depending on you're contrasting, depending on which one you think is higher risk, right? So the relative risk will be, you can take this ratio, okay? And this will give you something like
1.33.
let me see, this will be 0.19, 0.14, okay? So this is about this is about 1.36. Okay, so in fact, although the test doesn't reject the null hypothesis, but if you compute the relative risk, you'll find that actually in this group, right, women who give birth to child at a later age, right, there seems to be more of them having breast cancer, slightly more, about relatively is about 36% higher, okay? Right, this one is close to 20%, this relative to about 14%, right? So relatively the risk is about 36% higher. So this seems to be interesting, and actually people later did a follow-up study that's larger, right? And they actually found out that the statistical test actually rejected the null hypothesis of independence, right, with a larger sample size. Okay, so now it is generally accepted that as a woman has a child at a later age, they usually are at higher risk of getting breast cancer. That's why the doctors, right, when they want to examine for potential breast cancer, they will ask the patient at what age they had their first child. So that is also taken into consideration, right? It is, the risk is not very high, it's just slightly higher, a little bit. Okay. All right. Okay. So this is to tell you that when you do a statistical test, it's not just you just do a chi-square test and then give a don't reject kind of decision. Actually, you can go further than that, right? Check the relevant, depending on the context. In this case, the relative risk is worth exploring. Okay. All right. Okay. So all right, so then complete the following statement, right? So we reject or do not reject the null hypothesis of independence, right? We do not reject, right? All right, based on the test, women who had their first child at age 25 or older are 1.36 times more likely to develop breast cancer, right? Okay, based on the relative risk that we computed just now. Okay. this relative risk thing is usually of interest to the doctors and also of interest to the actuarial people, because when they insure some people, they might collect information that they can use to calculate the premium. All right, so they usually are also interested in this kind of risk factors. All right, because they will help them do calculations in how much premium they should charge a customer based on certain characteristics and based on a known risk that's reported in the medical literature, right? So just to let you know that, all right? Then the last question, question 4 is basically very simple. It basically is just a chi-square. So this is actually a real data. It is quite fun because it has it is real data and it's obtained from some historical event. So maybe you have watched the movie before, right? What was that movie? With Brad Pitt, the one with a lot of fighting. I forgot the movie. It's about the war between Achilles and Trojans. In that movie, Brad Pitt started as Achilles. So maybe you can check YouTube to see that movie, right? Anyway, this poem called Iliad is a Greek poem. So someone actually took time to analyze that poem and then recorded the number of battles that occurred there and in which the outcome is actually reported, right? So then, so the person actually arranged the data into injury site and whether the person actually survived, right? So you can see that the injury sites are broken down to 3 parts: body, head or neck, and limbs, right? And then survival, whether the person died or didn't die, okay? So actually, just by looking at the data, right, we know that there is association between, if you just look at the way the data is so unbalanced, right? You see that the fatalities are all on the side where you have body and head of neck, right? And then non-fatal with more associated with limbs. Even without doing a chi-square test, you know that this one is associated. Yeah? If you do chi-square test, you're sure to reject the null hypothesis of independence. Actually, this is not surprising, right? If the injury site is a body, like for example, you have a spear run through your stomach, right? Then it is almost sure to be fatal, okay? Or the arrow pierce the lungs and all that. It's almost sure to be fatal. And the same case with getting an injury on the head or neck, right? If there's the X falls on the neck, then the neck is severe, then of course the person is dead, right? So that's why you'll see that there are 45 instances where an injury was made on the head or neck, and 44 out of the 45 cases resulted in death. Yeah. So you know that hitting the head or neck is like a critical hit, right? A person will die almost surely. But the limbs is a bit better, right? More than half of them actually survive if the injury is at the limbs, right? The hands, the legs. Like for example, the hand got chopped off or the leg got chopped off during the battle, right? The person might actually live if this person can stop the flow, blood loss in time. Okay, so basically, even at the qualitative discussion level, we know that this will be associated already, right? But so you can carry out to do the chi-square test to confirm, right? And then which of the injury site is most likely to result in a fatality, which one less likely? So you basically just calculate the conditional probabilities, right? So for example, the probability of fatality I better just write on the whiteboard. Okay, so you have the probability of for the body condition on the body, right? So that will be, you just look at the row where you have the body data. So that's 67. 61 of them are fatal. Head or neck, those that are fatal are 44 out of 45. And finally, it's all right. So this one is 34, 13, right? Okay, so very clearly, you can actually punch your calculator to find the value. So, but then this one will be number 1, right? This will be number 2. This will be number 3. Okay. So easiest to die when it's hit on the neck. If you hit on the neck or head, the chance of dying is almost sure, almost 1, followed by hit on the body and finally hit on the limbs. Okay. And that actually conforms to true experience. Okay. So in a battle, don't get hit on the head.
Noted.
That's bad. Okay. That's why they have helmets, right? The helmets will protect your head from a blow, right? It looks silly, but it actually helps. Okay. So they know that, right? The metal helmets of that are worn by warriors in the old days, right? It protects the head. Okay, so I think this is a short tutorial, so we are done, right? So, so I think that's all for this tutorial. Have you checked with the lecturer whether there will be a tutorial next week?
Well, there's tutorial 11, but I'm not sure.
Sure, because we still have one. I still have one tutorial that's given by the lecturer. So possibly there's a last tutorial on. I don't know. There will be another tutorial in next week. All right. Okay. Right. Okay. So that's all for this week, and thanks for listening.
Thank you, Doctor.
Thank you, Doctor.
Thank you, everyone.